Rajamurthy sir. Thank you, Vinita ma'am. Thank you, Suji ma'am. Thank you, Ravita sir. Yes, thanks to everyone who are joining in, and the people who are joining us on our social channels. You can join directly live by using the Zoom link that is shared over email. Right. So let me do a hygiene check. If my audio is clear, type clear in the chat box. Great. Thank you so much, ma'am. Yes. So the format of these revision hackathons. Thank you so much, sir. The format of these revision hackathons is we are going to revise all the lectures in a sequential manner that are taken by the primary faculty. Here, either Rajiv sir or Jain sir himself. Right. So in today's lecture, we are going to cover the hypothesis testing, which is one of the important topics. So let me share my screen and point you in the direction of where we are in the course. Okay, great. I hope my screen is visible here. Now, if at all you log in into your Teachable, so we have slowly revised concepts from the first module, exploratory data analysis, make features. In the previous lecture, we have covered join and reshape data. In one of the lectures by Rajiv sir, we also covered the Seaborn library, the module, and all the different types of graphs. So I would request people who have joined here to also go through the explanatory visualizations, where you'll also see a few common Seaborn graphs again here. So we are not directly covering that because we have covered it in one of our Rajiv's lecture, right? So I would request you to go through that, and if there's anything, you can bring that to the next hackathon, which will be tomorrow. Even else, if there's something important, we are going to cover it as we proceed forward, right? So as previously told, there are quiz that are there, and there are assignments also, where you can see when we have finished to make features, there is also a make features assignment. I'd request everyone to go ahead and attempt it so that your concepts become strengthened. And there's also a sprint, and the explanation of the sprint also is there. So where you can revise whole of the concepts in a very small assignment that is happening here, right? So we're not doing the assignments right yet currently. We are going to revise the concepts. I would first encourage you to go ahead and do the assignments and sprints and quizzes by self. And later we'll come back to also go through them. Yeah. So now we are going to cover statistics. In that statistics, first we are going to cover the 2.1 hypothesis testing. In this lecture, you can see this was taken by Jain sir. Now you can see that here a lot of details have been covered, so which is 1.5 hour lecture. So we are going to revise concepts of that with a few references, right? So the lecture notes or the collab file is also available here. I'm also going to share the link of the same. So I request everyone to have the link open and running. Like I request you to run the commands parallelly so that the practice, because we are going to spend roughly 60 to 90 minutes. So better we can also run the queries and parallelly also understand them, right? So they become strengthened, right? So right now I'm going to clear all the outputs so that we begin. Okay. So now that we have, so people who have joined recently, so people who have joined us recently in this month or in the previous weeks, so do not worry. So these hackathons happen in a cyclic manner. You can go through the actual lectures that are there on Teachable, or even go through the revision hackathons, right? So you can even go through them parallelly. So there should not be a problem. You can go ahead and continue with the lectures, right? If at all you are, because we have this on 3 days of the week, AI hackathons, maybe you can parallelly cover, or even if not, you can attend both of them and catch up soon, right? So let's begin. I hope everybody has their collab files open with them, right? So if you have your collab files open along with you, type O in the chat box. Sorry. Yes, I hope everybody. Yes, thank you so much, Rajendra sir. Thank you, Anita ma'am. Thank you. Thank you, Anita Devi ma'am. Thank you, Sujata. Great. So now what we're going to do, we're going to proceed through the lecture. Now, if you see the hypothesis testing, now what happens is till now we have just understood how to work with different functions and modules of Python and a few models of different graphing and a few modules of pandas and numpy. Now we are going to get into a little of the data science modules. Now you can see that here what is hypothesis is basically whenever you are trying to take a sample, right? So whenever, for example, if it's you can see that there is survey of elections and all, you many times these survey results are way ahead of the election campaign, are given out on news channels and all. So how do they do that? They survey with a specific method and do that across different sample sets, and they come towards a hypothesis. They're not concluding anything. So we are going to cover in hypothesis in this particular lecture 1 and 2 sample t-tests. So we are going to understand more about it. So these are two ways to go ahead and do hypothesis testing, right? So the objective is to explain the purpose of this t-test and identify where it is applicable, and we are going to set up and run one sample t-test, right? So if time permits, we're also going to do the two sample t-tests, right? So basically where we compare two different samples, right? So here even Jain sir starts with this quote. It says, if you want to make an apple pie from scratch, you must first create the universe, right? So yeah, Raja sir, so if you've joined recently, should not be a problem. Here, because this would be in amidst, like you would be kind of parachuting into the concepts. So what I would request you is start from the module 1 here, right? If you've very recently joined, in that case, you can start from here. Because we have many people who have started from scratch. So I request you to first go through these modules, right? So once you log into your Teachable, you come to your basics refresher and slowly start building the concepts, right? So the team would also will get in touch with you and share, the actual flow for how to go proceed forward, right? So it should not be a problem, sir, right? So to get a feel of it, if you choose to go through it to understand the application, you can still continue and be here. Thank you so much, sir. Yeah, so basically what we are referring to in this particular example, here is, right, you need to have a bigger, larger data set to even make a small output out of it, right? So we'll try to understand what type of predicted data, based upon what type of data we have different type of hypothesis testing methods, right? So now if you see, if there is categorical data or there is numeric data, right? So today we'll be looking at this left side portion where in the categorical data we are trying to do this one sample t-test and two sample t-test where we have a little numeric data and also a little text data or other categorical data as well, right? So based upon what type of outcome we choose a method, right? So if we are, we'll come across these methods as we proceed. So right now you just get better. Let me, yeah. So if possible, you can go ahead and mute. Yeah. So we are we'll be going across this chi-square t-test, good test. These are all tests, but right now we are going to cover sample t-test, one sample t-test, and two sample t-test. Right. So which comes into this type of data where numeric data is available. Right. So I would, just because to avoid confusion, I'm not going across all the other different types of tests or hypothesis testing. We're going to just go forward into this numeric data type outcome in categorical data, right? So we are going to look at a few examples where a few examples like comparing the sugar or caffeinated sugar values in Coke and Pepsi and all those such examples, right? So first, before that, in our okay, so let me just check if my screen is visible. Okay, so just before we start, we'll try to set a few definitions, right? So a few of the definitions we have seen while we have, understood a few of the modules from Rajiv's lecture, right? So now one of them is like this, what is normal distribution, right? So let me show the graph of normal distribution. Now, when you look at a normal distribution, this forms a bell curve, right? If you remember, we have done that example of Titanic curve and all those examples where some random graphs, histogram graphs we have done, where we try to, the data kind of sat into this normal distribution, right? So we have seen that thing. So this is normal distribution. Whenever you find this bell curve coming in, so it is going to be this normal distribution. And in that we have standard normal distribution, right? So now what a standard normal distribution is, whenever the mean, the actual mean is going to be centered around zero, like if it is going to be zero, the mean is going to be zero, then it is called a standard normal distribution, right? So which means that there are a lot of data points, and when you are plotting a graph, the mean of all of the, the mean of all of the inputs or the observations show up towards the center, right? So that is what is a standard normal deviation, right? So this is what we have understood right now about normal distribution, standard normal distribution. And first we'll go ahead and try to understand what is an inference, right? So before we get into the testing and all, inference is nothing but basically, even Jay sir also gives an example. Like for example, if it is cloudy out, maybe we would be inferring, saying that, okay, it might rain. Or we can also maybe infer, if it rains, there would be power cut in a few areas also, right? So whenever you extract some particular insight out of that, so that is what we are referring to inference here. And in that inference, statistical inference is the act of generalizing from a sample to a population. So meaning, for example, we wanted to do let's say election campaign, who would be coming up with the probability of somebody winning, right? In a whole bigger population, it is very difficult to actually go and sample or survey it. In that case, what we do is we use statistics and do the analysis on a sample data, right? So based upon this sample data, we are going to infer what could be the actual result of a bigger population set, right? So the statistical inference is the same, where we are generalizing from a sample to a population with a calculated degree of certainty that we are going to be sure, like 95% of the chances are that so and so person could win or something like that, right? So if it is clear that the statistical inference is you're going to infer from a sample data and try to come closer to the actual result that would be from a bigger population. If that is clear, type C in the chat box. Thank you so much. Thank you, Sujana. Great. So now we've understood what is statistical inference. Now we've understood about the bell-shaped curve also, right? So even in our previous hackathons, if you see, we have done 2 random distributions where such a curve, when we plotted a histogram, such a curve was also, we got such a curve, right? So now what we're going to do is we are starting to understand with one specific data set here. This data set has all the temperatures, right? So this body temp.csv. So let me try opening the CSV. Okay, did it copy the whole thing? Okay. So if you see, it has ID and different people are there and it has their temperatures measured here, right? So different IDs and different temperatures. So now we are going to import pandas as PD, the alias, numpy as NP. Now what we are going to do here is we are going to create a new data frame. The name of the data frame is temperature. And we are going to read _c. We are going to read the CSV from the URL given and loading it into the temperature data frame, right? So let us see how many rows and columns we have in this particular temperature data frame by using temperature.shape, and also see first 5 rows of it, right? So if Raja sir, you're there, so we have discussed what these functions do in our previous sessions. So let me just do not try to try to understand whole of it. You'll be kind of overwhelmed, but these are a few commands which give you some specific output that we are expecting, like temperature.shape will give how many rows in column, temperature.head. So this function is going to give us the first 5 observations or rows of that particular table, right? So I'll be sharing with you personally on what specific sessions you can go through, sir. So not worry, right? So I'm going to run this. Now we can see that we have 223 observations, 223 rows in it, and 2 columns. 2 columns is something that we were able to understand, right, from the data set here. And now there are 223 people's temperatures that we got, right? So and this is how the first 5 rows look. Okay, so if at all we want to see a few important statistics about it, we are going to use the .describe function over the data, right? So we can see that the count is 223, the mean is 98.16, right? So yeah, thank you so much, Raja. So what is actual body temperature? What should be an ideal body temperature? Can anybody mention it on chat? Yes. So here 98.6. Thank you so much. Yes, Anita Devi. I think Aparesh, maybe I should also check. I think it is 98. So 98 is something we are clear, Raja said. Maybe we want to be specific. Now, Anita ma'am, I think 98.6 is a little accurate, right? So now what we are doing here is the mean of this whole data set, right? Now you see this whole 223 people average that is coming out to 98 here. And there are other important stats also, which we are not, trying to understand. The minimum of this temperature was 96.7. The maximum was 99.6, right? Thank you so much, sir. Now, what we are trying to do here is, so we know that this particular module, the matplotlib, is also something which is useful like Seaborn, where we are going to, which will be useful for us to plot graphs, right? So here what we are trying to do is, first I am going to plot. So here we are using the PLT as an alias. So instead of every time trying to write matplotlib dot pyplot every time, we are going to say PLT. So that is why this as or alias step is helpful. Now every time we can just say plt.hist. Here this will generate a histogram, right? On what column? Body underscore temp column from the data frame temperature, right? So I'm going to run that. Now this is the histogram, right? So this is how, because we have lesser number of data points, and most of them are between 96 let's say 96.7 to 99.6. The graph looks like this, right? And here we also try to understand a little bit more about skewed graphs, right? So let me bring that reference point here. Okay, so now because here we do not have X and Y axis, so what I'm going to do is I'm going to bring back these. We are going to say plot dot Y label. We say this as frequency, and we are going to say plot dot title, which is this distribution of human body temperature, right? So when I run this, you can see that distribution of human body temperature became the title, and here is the frequency. And here we know that these are the temperatures. Okay, so let me bring this reference, which is useful. Okay, we are here, right? So now if you see, we want to understand something called skewness. We know normal distribution is bell curve, right? But what happens is not every time all data seems to be bell. Sometimes it is a little skewed, or towards right or left, right? So we'll try to understand. Like first, let us look at this right skewed, or which is also known as positive skewness, right? So what happens is, like if you plot, let's just say population of India and age here, right? So we can see that most of the population would be the younger population, and if you're starting from, let's say 0 to let's say 100, or say some number, so it is going to have it will not be balanced normal distribution, right? So we have more younger population, so that is where this is skewed towards right, or it is also called as positive skewness, right? So now by numbers, how do we try to understand? Now you can see here, if the mean here, the mean is, because the mean would be the center, the mean, if it is greater than mode, right, meaning the highest number here, the distribution is positively skewed. So we are trying to measure if it is positively skewed or left skewed or negatively skewed. You can see this is how you'll get. So before understanding the mean, median kind of numbers by numbers, if you understood the example, what is skewedness and what is positive skewness, if you understood that, type U in the chat box. Great, thank you so much, Ravindra sir. Now, so this is what is it. Similarly, there are a few examples where it is left skewed, where maybe if you are trying to plot any of the other examples, right, where the data is more left skewed. Like one of the examples JSR says is like, let's say COVID. We are trying to map COVID, and then with age plots and all, then then you can see that that particular graph would be left skewed, right? So that is what we can understand, right? So this is how the left or right skewness by graphical depiction you will understand. But if at all we want to understand it by numbers, we'll see that whenever the mean, the center is less than the highest, the mode, right? If whenever the mean is less than mode, the distribution is negatively skewed, right? So this is what we've also understood. Now, like if we come to this particular example, now even this graph would also not be exactly normal distribution, right? So we'll also come plot a graph. We'll try to understand how skewed it is. Is it right, left, and all, right? So the easier way to see it is here in right skewed. You can see that it is flatter towards right, and when it is left skewed, it is flatter towards the left, right? So you understood that. Now we've plotted a histogram of the 222 rows that we had here, right? So now we've got a plot. Now what we are trying to do here is trying to get mean and median, right? So because that will also let us know if it is left skewed or right skewed, right? So we are going to get how we are going to, on the data frame temperature, which has these 223 records, out of the column body underscore temp, we are going to operate the function dot mean. So, and whatever output will come will be saved in temp mean, and similarly dot median function will give and save it in temp underscore median, right? So I'm going to run it. Okay, so now I'm going to print these both temp mean and temp median, right? So now you can see that there's a very slight deviation here. Now mean here is slightly lesser than median, right? So if we come to the graph here, whenever the mean is okay, so we have a mean and median example also. So mean is less than median, so the distribution is negatively skewed, right? So it is slightly flatter towards the left side, right? So we also have something similar here happening. The mean is lesser than median, right? So maybe visually it is not very is apparent, but you can see that it is a little flatter towards here, and the graph, if you plot it, it would come this way, right? It's not normal like this. It will come in this particular way, where you can see that there is a little more flatter towards left, right? So because we'll not be able to make out from the graph, it is better to go by numbers here, right? So now you can see that mean is less than median, right? So in that case, this is a little left skewed, right? So if you understood that this particular data set that we have, the distribution is left skewed. If you understood that, type U in the chat box. Yes, thank you, Sujana. Thank you, Ravindra sir. Great. Now we'll go forward and thank you, Vinita ma'am. We'll go forward and try to see a little more plotting. Here we'll do samples, right? So we are going to do samples of the actual population. Now let's just say the total population is 223. We are going to validate our assumption, all of this by considering the 223 population as the whole larger set, and we are going to take a fraction of the set and do tests over that and see if it is matching our assumptions, right? So here there is one particular function, one particular parameter that we can use. So whenever you are creating a new data frame, here we are going to create a sample data frame out of the temperature data frame. And here what we are going to use is, we are going to say dot sample, and within brackets, you're going to say fraction 0.1. So what this command is going to do is, it is going to, out of the 223 rows, fraction, meaning 0.1, which is 10%. It will take 10% of that particular data set and save it in the data frame sample, right? So let us try to first run this and then try to get this shape of the sample, right? It should have 10% of the records, right? So we understood that the first 5 records are like this, and it is having 22 records only,
right? So now with the help of this sample within brackets, we are saying fraction FRAC equal to 0.1, and we are able to get a sample out of this. So now what happens is whenever you run this, it will take any fraction. It is not going to take just first 5 or last 5, right? So I'm going to run it again. Right, so it is going to generate, many times different. So because we have saved it in the data frame, it is trying to, it is showing whatever is there in the data frame, right? So, but what this particular command does is going to take a fraction at 1/10 of that particular data set and plot it, right? So now we have the sample data set with the same column heading body underscore temperature. Now we are going to do dist plot and we are going to run it and see how this plot is going to look, right? Yes, so now if you see this, this particular example, it has 22 records, right? So in this, the left skewness is little visible in this particular fraction. So this is not equivalent to this. This is the whole, right? Now this is only a fraction, which is a 0.1, right? So let me run it again. So now if you see, this is a different fraction of data set, right? So every time you run, this fraction will give you a different fraction, which will help you understand, various other combinations of different data sets. So you can randomly check how is it looking in various different sets of data, right? So you can consider this like this. Like for example, this, if you're trying to do the election campaign survey only, if it is the whole data set, this is how the distribution is like. This could be, let's say, one district. This could be another one. This could be another one, right? So this is what is happening. We're every time generating a fraction of it and running a dist plot over that, right? So now we have understood that we have created a sample, and we have understood that the sample has different sorts of data in it, right? So if you're clear there, we'll try to freeze on one of the sample and try to get mean and median of these samples, right? So now what we are trying to do is we are trying to do our assessment on samples and then see if we are matching closer to the actual data set, right? So which will clear our hypothesis testing concepts also, and we'll also have an example, right? So I'm going to do the same that we have done with the bigger, larger data set. I'm going to do the mean and median, but here on the sample, right? So let me do that. And I'm also going to print them. Print temp underscore mean, comma, temp underscore median. Okay, so now you can see that this particular sample, the mean is 98.2, and this is higher than the median, slightly higher than the median, 98.15. So if we come to skewness, when mean is higher than the median, it is a little positively skewed, right? This sample that we have taken has more temperatures that are on this side of the graph, right, than this side of the graph. That is what this means, right? So now we have taken our sample, and now we have understood that this is a little positively skewed, right? So the whole data set is left skewed, but this sample is positively skewed, right? So now we understand that. So now what we are trying to do here is, yes, so yeah, so now what we are trying to do here is we are going to, hi Anil sir. So now what we are going to do in this sample data frame only, and the fraction, we are going to do the dist plot. We have already done it, right? We have got the median of it. Now till here we are clear. Now we are going to do a graph, and in that graph we'll also see this, what this AXV line does, right? So what this does is it is going to plot one particular vertical line. So you can see that when I'm hovering on this, it is giving me information. What does it say? Let me hover. It says add a vertical line across the axis, right? So now here we are saying add a vertical line, and the vertical plot that vertical line where it is temp underscore mean. So let me plot and then show. I'm doing the plot. Now in this plot, what is happening is we have plotted in gray temp underscore mean and in black temp underscore median, right? So just because they are a little closer to each other, you might not be able to see the difference here. But what we are trying to do here is we are trying to plot them, the axis, the vertical line over this, right? So let me try to so when I'm running again, you can see that there are two lines here. One is a gray line, one is a black line, right? So which is mean and median, right? So this AXV line is going to plot a vertical line, right? Wherever you give. So for example, instead of temp underscore mean, I'm going to say, I'm just saying 97, okay? Just to give you an example, right? So I'm going to run it. Now you can see at 97, our graph, a vertical line came in, right? So instead of 97, what we have given is a temp underscore mean, which is plotting mean of that particular sample, right? Sometimes they are very close. So yeah, so in this particular example, you can see the median is lesser than the mean, right? So this will give you a little idea on the skewness, right? So instead of every time trying to go by numbers, we are trying to visually see if the median is higher or lesser than mean, right? So this is what we have done. So if you understood this particular method, AXV line, and how to use it, if you understood that, type U in the chat box. Thank you, sir. Thank you, sir. Thank you, Ravindra, sir. Thank you, Anita ma'am. Thank you, Anita. Right. So it becomes easier. You don't actually have to see the numbers. You can visually see, okay, yeah, here black line means median and median is lesser here than mean. Right. So here, this particular line is just naming the temperature, like, so it is just saying body temperature in degrees, and whatever mean is there, we are trying to print it here. So 98.07 Fahrenheit is the mean, right? So now we are able to plot it here. So we'll go forward and we'll try to understand this one example. Just there are two important things that we need to understand. Okay. For some reason, they are not here. Okay. So let me bring that link as a reference here to you. Let me introduce you to this concept, which is central limit theorem. And yeah, so I hope my screen is visible. So we are going to understand a little about central limit theorem, right? Yes, thank you, Raja sir. So you're catching up nicely, at least on the overview, even though you have parachuted into the session. Thank you so much. So before we proceed on to actually going further, now we understood mean, median, skewness, and everything. Let's try to understand a little more concept. One of the concept is called central limit theorem, and another one is law of large numbers. I think law of large numbers is here. Okay. So now what law of large numbers says is, it's a very simple, it's a fancy name, that's it. So this it states, the more, as we take more samples, whatever mean that is coming, like as more number of samples you are doing, the mean of actually all of the samples outputs, whatever you are getting, will be closer to the actual distribution, right? So what law of large numbers saying is, as we take more samples, we expect the mean to get closer to the actual mean, right? So which seems, practical, right? So if you're going to take more and more samples, right? So now I am going to take, this was one sample, and every time we are going to do many samples like that, and you're collecting means from there, right? So there are a lot of samples that can be generated, because we have, every time we are generating sets of 22 from 223 records. So there are a lot of sets that can get generated, right? So very large number, because that, that permutations and combinations, if you see, there will be a large number of sample sets that can be created out of this. And if you take each sample's mean and do a mean of the whole outputs, right? So the more number of samples you're taking, the mean, the average of all that samples means will be closer to the actual output, right? So this is a law of large numbers. Let me show you this visual. Law of large numbers, right? So what does law of large number states is, if you run many trials in a simulation or experiment, the probability will get closer and closer to the actual or theoretical probability of the event, right? So if this concept is clear, the law of large numbers, type C in the chat box, right? So which is simple, where the more samples we take, the mean of all of it will be closer to the actual average, actual mean, right? Thank you, Suja ma'am, right? Thank you, Ravindra sir. So this is law of large numbers. And parallel to that, there is, thank you, Raja sir. There is another hypothesis, another thing like that, which is called central limit theorem, right? Which also says the same thing, but in a different way, right? So what central limit theorem says is, when the large sample size, the samples will be normally distributed, and the mean of the sample will be approximately equal to the mean of the whole population, right? So there is a very slight difference. What law of large numbers saying is, the mean average will be approach the actual mean, right? Will approach the actual mean. So here what we are saying is, the mean of equal, the equal of mean, all the distributed samples, whatever is there, it will be normally distributed, right? So I think there's a diagram also here. So what it says is, central limit theorem says is, so if you take many samples and each sample's mean you get, and if you make a graph out of it, here you have collected, in law of large number, more samples get you closer to the actual mean, that is clear. But you have, if you plot a graph of it, all of the samples that you're getting, it will be a normal distribution, right? Normal distribution we understand, right? Which is a bell curve, right? So which is like more of these are, similar theorems only, similar laws. What the central limit theorem says is, the more all of these samples, whatever is there, if you plot a graph, it will be a normal distribution, right? So this is what central limit theorem says. Just to clarify, I am going to give you this example: central limit theorem versus law of large numbers. So the central limit theorem states that when sample size tends to infinity, like we keep on increasing the number of samples, the sample mean will be normally distributed. Here where central limit theorem is talking about the graph. The law of large number states that when sample size tends to infinity, meaning that we are going to keep on doing more samples, the sample mean equals to the population's mean. Here it is saying it will be near to the population. Here it is saying it will be normally distributed, right? So if you're clear with what central limit theorem is and what law of large numbers is, write C in the chat box. Great. Okay. So thanks everyone. Thanks, Ravindra sir. Thanks, Vinita. Right. So we'll also test this for our samples, right? We have a lot of fractional samples of 22 sets and a larger sample of 223. So if we are able to do it for our example, we know that these are also true, right? So this is why we do a lot of sample sizing, even when we are going to do any statistical analysis, right? So now we have understood both these laws. Now here we have mentioned is in central limit theorem, two incredibly important things to keep in mind when we are talking about central limit theorem. It tells us about the distribution of means, right? So the graph is of the means, right? It is not of the actual observations. The populations, let's say if you're talking about temperature, the population's temperatures could be different, like it cannot be normal distribution, right? But what is normally distributed is the means of all of these data sets will be normally distributed. So it tells us about the distribution of means, but not actually not the actual observations. This is one thing that we have to remember. It tells us that as we take more samples, the mean of the sampling distribution approaches or better approaches the true mean of the population. So we have understood this also, right? So now this is what is there, and we'll go forward and try to understand this. And this is the actual base of many statistical analysis. That is why people do large number of smaller samples instead of trying to do a bigger sample, because it will be resource heavy also. If at all you want to have people going surveying whole of the India, it will be very cumbersome and will not be easy, right? And now because if it is digital, if people even you do not have to deploy the resources, you can do that spread across and can get the inputs. Not all cases, few cases. If you have to go and collect temperature, then you have to have people and collect the data, right? So that is how it is. Yes, so Ravindra sir asked how the two will be used and final difference between the two in application. So basically, sir, both of them say the same thing in a different way, sir. So one is talking about the means having a distribution which is normally distributed, and the other one saying the more samples you take. So you can, this is the actual thing that you can say. So the more samples you take, each of the samples result, and if you do the average of all the samples, right? So let's just say here there was an example of coin flip, right? So let me just go ahead. I just glanced through one example, which was a coin flip. Okay, so coin flip is an example where it has only two outcomes. But now what happens here is that the more number of samples you take, you are going to approach the actual thing. So this is commonly applied everywhere, even in all the analysis, surveys and everything, right? So even in our case, we are going to test it and we'll see how it is true. Right? Thank you so much. Now we have understood this concepts here. Now we are going to understand this T distribution, right? So while the central limit theorem works perfectly in theoretical math land, in practical reality land, distribution of sample mean isn't exactly not always normal, right? So instead, the sample mean follows what is called a T distribution, right? So we have seen this distribution, which is the standard normal or normal distribution, right? So now T distribution is something that becomes flatter, right? So these are like kind of becoming flat, right? So when this particular number is decreasing, when the frequency of when the number of observations is decreasing, so you can see that T the curve will become a little more kind of shortened, right? So that is what we are talking about in the T distribution, right? So the T distribution has a smaller shape to the normal distribution. So if this is the normal distribution, the T distribution will be a little similar in shape, but it will be shorter but it is able to flex depending upon the sample size. So that is what we are going to see. Now, this T distribution was discovered by this person, William Seeley, when he was working at a brewery, right? So where he has seen, maybe even Jay sir explains, because he was in a brewery, he was trying to see that the taste of any particular wine or beer is fading, as time progresses, right? So I mean, the beer specifically, that is what he graphed out, and that is how he came across or discovered the T distribution, right? So this is how it kind of gets reduced. So this is T distribution. We'll also go through this with an example, right? Yeah, so now we've understood about the statistical analysis. Now, a few examples of populations we'll try to understand. So all residents of the United States are over the age of 18. All NBA basketball players, all people who have had influenza vaccine. So if you are trying to take a bigger, larger population, it could be a set, right? So if at all we're talking about one data set, which is all people who are between ages 18 to 45 or 60, right? So this could be a larger set. That is what we're talking about, population, right? So a bigger set is nothing but a population, right? And now for pi, I mean, what we mean here is the particular single test. Yes, Vinita ma'am. So we are going to do the distribution of samples, and in real examples, not every time it is normal, right? So it is sometimes as the shape mentioned here, right? Correct. So we are going to do with an example. An example will clear all of it, right? So now, if this is the larger population, what is an hypothesis, right? So the mean age of all US college students is 23. Let's say this could be either true or false, right? Now this is an hypothesis. So there are you can do any hypothesis like that, which is a hypothesis is nothing but your initial assumption before you do a test, right? You can say you visit a school and say, I think the average grades of this particular school students is say 56. So it is an hypothesis, right? So if you go ahead and test it with if the hypothesis is right or wrong. So now let us try to understand what is t-test. A t-test is a systematic way of weighing evidence for or against an existing claim or a hypothesis. Existing claim meaning hypothesis about a population parameter, right? So this could be one hypothesis, like let's say the mean age of all Indians is so and so. It is an assumption that we are making. So now t-test is a way of stacking out or weighing evidence for or against this claim that one person is making or an agency is making, right? So if you have understood what is t-test, which is nothing but this a way to put out evidence to in favor or against a claim. So if you understood this, type U in the chat box. So we are going to do a lot many tests. So t-test is a way to check that. Now, when you plot those t-tests, the graphs could be in this particular manner, right? Okay. Thank you so much, Suj ma'am. Thank you, Vinita ma'am. Thank you, Ravindra sir. Right. So let us try to test. First, we'll make a few assumptions and we'll work with a new data set and see, we'll do multiple tests and see if our hypothesis, what was there, was right or wrong, right? So let's see this example. Now, in this example, we are working with a data set, which is this related to Coke, right? So it is what we are doing is there are two columns in it. One, the number of drinks that it has 50 rows in it, and the caffeinated sugar values in that, right? So all of that is there in this particular data set. Now, what is our hypothesis about it? What is the whole population? We'll try to understand, right? So the source is, so this person Garand and Bell, what they are saying, caffeine content of a fountain. So basically in US, sometimes, not many times you get the, drink in a tin, but many places it is in an open fountain where you can, you will have a tap, and or you can, get the Coke directly from the fountain, right? So now what we are trying to do here is the caffeine content of fountain and private label stores. So all of that is there in this data set. So if at all you have taken 50 Cokes like that, each of the caffeine was measured, and this is what is the data set, right? And this could be spread across different areas. Like let's just say if it is in one particular store, if the caffeine value was 47.32, and it could be in another fountain, it could be different value, right? So this is like a data set like that. So now soft drinks like Coke and Pepsi are manufactured to have a standard caffeine content. For example, 12 oz serving of Coke has 34 milligrams of caffeine, and a similar 12 oz serving of Pepsi has 37.6 milligram, meaning Pepsi has a little more caffeinated sugar than Coke, right? It should be standard set values like that. However, fountain soft drinks are typically mixed in individual restaurants, right? So the restaurants are going to mix it in dispensers. So it is more difficult to maintain a standard level of caffeine per serving, right? So because it is mixed by individual restaurants, it is definitely not going to be standard, right? So now we got the data of it, right? Now let's go forward and try to understand. Imagine you are in a quality assurance role at Coke, assigned to ensure that franchisee restaurants that serve Coke beverages are maintaining product consistency. Or else what happens is the taste of the drink or Coke looks different every time, right? So in particular, you wish to ensure that Coke mixed in a fountain soft drink dispenser has the standard caffeine content of 34 mg per 12 hours, right? So as in a standard 12 hours can of Coke, how much ever is there, if you are a quality assurance person at Coke, you'd want the same in a fountain drink also. If the caffeine content is heavily different from 34 mg per hour, that indicates managers of the franchisees should be retrained, right? So this is our whole setup, right? So now we understood the soda data contains 50 records of samples of Coke collected from different franchisee restaurants, right? So if you have understanding of the data set about this Coke and this in individual restaurants mixing it, if you're understanding of this data set, type U in the chat box. Great. Thank you, Sujana. Right. So now let's proceed. Thank you, Raja sir. Thank you, Anita ma'am. Now, what we are doing is we are creating a data frame, and in that we are importing our data, right? So, and let's go ahead and print that particular data set. So we have drink and caffeine in that data set. We have 50 rows and 2 columns. We are clear, right? So now what we are trying to do is hypothesis and significance level, right? So we'll try to understand first the hypothesis, right? So the initial hypothesis that is made is called the null hypothesis, right? So the hypothesis that the average grade of the school is 56 is the initial hypothesis. It is called as null hypothesis, right? So the null hypothesis is a one sample t-test. So in a one sample t-test is that the population mean is equal to some reference value. Like here, what we want our reference to be, right? So let us try to come here in Coke example. The hypothesis is we want the mean of all these drinks to be 34 mg, right? The caffeine in all of these things to be 34 mg. So this is the initial hypothesis. We wish to test the hypothesis that the mean caffeine content in all fountain Cokes is 34 mg. So the null hypothesis is denoted as H0, right? So now this is it. In my example, if say we are saying the null hypothesis, the average grade is 56 of the school, the H0 and mu is equal to 56, right? So that will be 56 marks. So this will how the hypothesis will be. Now we have understood the hypothesis, right? So there could be different data sets, and every data set, whatever claim that you are initially having in mind, is going to be called as the null hypothesis. If you're clear about null hypothesis, type C in the chat box. Great. Thanks, Prashant. Thanks, Ravinder sir. Thanks, Vinita ma'am. So now we have understood null hypothesis. Now, what is alternate hypothesis? If that is not true, that is alternate hypothesis. If average grades of that school is not 56, if the average caffeine in all these cokes is not 34 mg, then it is the alternate hypothesis, right? So this is also clear. Now we've understood hypothesis. Now we've understood alternate hypothesis. Now it could be either one of them. If it is true, it will be our hypothesis was true, or else the alternate hypothesis is true, right? Now there is something called significance level, right? So let's try to let me share this one reference where significance level will become clear to you, right? This will be, I think, mostly the last theoretical concept. Then we'll go into graphs, right? So now, what is significance level, right? So now, if first let us look at the graph, right? So now, if you look at this graph, now all the distribution, if it is like this, towards left and right, it will be skewed. Like it will have less records towards the beginning and less records towards the end, right? So now, what we are trying to do here is, what is confidence level? The probability with which we will accept a null hypothesis when it is true is confidence level, right? Meaning, if we are saying the confidence level is 95%, we are saying if confidence level is 95, we say there's 95% probability that the null hypothesis is true. Okay, so this is confidence level. So it is denoted as like it is denoted as 1 minus alpha. Let's try to understand what is significance level, right? So now we understood this portion, confidence level. We mean that more chances that it is between, it's not towards the end, it is within the range, right? So that is confidence level. So the significance level is the probability with which we will reject a null hypothesis when it is true is the level of significance, right? So let us continue. It is denoted by alpha. In standard terms, we use 1% significance level, 5% significance level, 10% significance level. So the significance level, also denoted as alpha, is the probability of rejecting the null hypothesis when it is true, right? So what is the probability that we will be rejecting the null hypothesis is significance level, right? So confidence level is the probability with which we will accept a null hypothesis. We're confident about it. And the opposite of it is the significance level, right? So I hope these concepts are clear, right? Significance level and confidence level, right? So now there is the p-value. P-value or calculated probability is something that we are going to calculate. Is the estimated probability of rejecting the null hypothesis of a study question when the hypothesis is true. So we'll see this by example. Now we've understood significance and confidence level. Let us go and read through this, right? The significance level is the threshold that we pick to determine whether we reject or fail to reject our null hypothesis. The significance level is often set at 0.05, meaning 5%, but it does not have to be, right? Like the example we have seen. In some areas where we want more confidence, the significance level, we cannot tolerate, it not being, the null hypothesis not being true. Like if you want it 99% to be clean, right? Or 99% of the time, like if there's something that where you want higher standards of confidence, then significance level will be lower, right? So 5% significance level is something that we are having here, right? So there are chances that the null hypothesis could fail, right? So we are going to do this mathematically. Now, we always write our hypothesis and pick our significance level. We do whenever we do an data analysis, right? Okay, so the general idea behind the t-test, right? So whenever we are going to do the t-test, now what the central, by the central theorem, mathematically we know that if the mean caffeine content in all fountain soda is 34 mg per 12 hours, most samples we take from that population will have a mean that is very close to 34 mg, right? So if the mean caffeine in all fountain soda is 34, most of the samples that we take will also be roughly similar to 34 mg. By the central limit theorem, most samples will have a mean range, will have a mean in this range, right? So this was our confidence level, and this is where the significance level is, right? And very few will have a sample mean that is much either higher or lower than 34 mg per 12 hours, right? So now we are trying to understand the confidence level and significance level by this graph, right? So by central limit theorem, if the actual caffeine here is 34 mg per 12 hours, only a few samples will have either too low caffeine or too high caffeine, right? So if you understood this, you understood these two graphs, right? So when we calculate the mean caffeine content in our sample to get a sense of how much larger or smaller it is, then we'll understand, like, while we are trying to test the null hypothesis, right? Okay, so let's get into trying to understand what is the mean actually. So everything is around mean, right? So now we have our data frame, and in that data frame, we have 50 records. So what is the mean of that caffeine, right? So now we have seen that, okay, so it is coming up. So the caffeine is 37.94. And what was the initial hypothesis? What is that we want? We want it to be closer to 34 mg, right? So the mean caffeine content in the sample fountain we have collected is 34.9 mg per 12 hours serving, right? So this is where we want our, this is where our hypothesis is, and this is what the mean is currently, right? So now what it says, the t statistic and the p value. A t statistic is a measure, so we'll just understand what is the t statistic and p value. A t statistic is the measure of how different our mean sample is from the mean under the null hypothesis, right? So you can see that this t statistic is how different it is from the mean, right? So the larger the t statistic is in either positive or negative direction, the less likely is that we would see our sample mean if the null hypothesis is truly correct, right? So if it is closer, better. If it is farther, our null hypothesis is going to be rejected, right? So this is what we've understood here. Now, the p-value is the probability of observing our sample mean if the null hypothesis is correct, right? So we are going to test that. So p-value is something that we are deducing. Now, if p-value is not the probability that the null hypothesis is true, right? So if it is not true, the p-value is that probability that will not be true. Okay. Okay. So now we've understood these. Now let's try to get into the code. You don't have to actually every time do this mathematically or graphically. There is a module in Python, which is stats.ttest_1sam, right? So here, if you do this over your data frame, you'll be able to get the variable, the t statistic value and p value. Here, you don't have to do it mathematically, do this all math and all those things. You can go ahead and use this function, right? So functions are here to make our lives easier. So now putting it all together in our code example. Yes, Vinita ma'am. Yeah, so we are just closer, ma'am. So Vinita ma'am asks if the null hypothesis is accepted or rejected, right? So we are very close. Null hypothesis was it is 34. Alternate hypothesis, what? It is not 34, right? Now we will reject the null hypothesis if we have a p-value less than our significance value. If our p-value is less than 0.05, then we will reject the null hypothesis and accept the alternative hypothesis, right? So let us try to do this by our newly discovered function, right? So we are going to use st.stats.ttest underscore one sam. Here I'm going to give the whole data frame, right? So we are going to give the whole data frame. And then our initial hypothesis 34, right? So when we are going to do that, I'm going to run it. Now you can see that it has given me an output, right? So the t statistic as 5.31 and the p-value 2 point something. Here you can see e to the power minus 0.6. So e, what this means is 2.6 into 10 power minus 6, right? So which is a very smaller number. So because the p-value, now if you see this example, right? So where we had our, if p-value, now the whatever p-value is there. Yeah, so let me come here. Because the p-value is less than the significance level, we reject the null hypothesis, right? So Vinita ma'am, by our own understanding, because it is 37 way out of our mean, we might in mind think that we would reject it, but mathematically we would want to do that because this is a smaller data set, we could reject it by ourselves. But you can see that because the p-value, whatever we got from this particular function is far less than 0.05, right? Then we are going to reject the null hypothesis, right? So and conclude that our alternative hypothesis is correct, that the mean caffeine content in all fountain cokes is not 34 mg, right? So if you have understood this, like except for, I'm going to repeat this this particular example portion, but if you have understood that when it is rejected, when the null hypothesis is rejected, when it is accepted, if you understood that, hold it there, right? So if it is way away from our mean, it is going to be rejected in positive or negative direction. Now we have a function which is stats.ttest underscore one sample. Yes, Vinita ma'am says good. Stats.ttest underscore one sam, where we are going to give our whole data frame and what is our initial hypothesis, mean under the null hypothesis. So we have given 34 and whole of our 50 the data sets that we have given, right? Then we have got two outputs. One is p-value and one is t statistic, right? So we are more concerned with this p-value, right? So many times, just by seeing the values, it will be difficult for you to, here in this case, maybe you'll be able to say that it is not closer to 34 mg. But if you are looking at a larger data set like population of India, you need something more concrete like a number to tell if it is right or wrong, if the null hypothesis is correct or not, right? So whenever this p-value that is coming out of this function is less than this significance level, right? Whenever it is less than that significance level, you will reject the null hypothesis. That is as simple as that, right? So even, as we go forward, there's another example to it, and that will conclude the session. We'll check another example and we'll clear that, right? But if you understood out of this function, whatever p-value comes, if it is less than the significance level, we are going to reject the null hypothesis. If that is clear, type C in the chat box. Thank you, Suju ma'am. Thank you, Vinita. Thank you, Anita. Yeah, so now we've understood till here. Now common mistakes. Because the p-value is less than 0.05, we fail to reject the null hypothesis and conclude the mean caffeine content is not 34. Failing to reject the null hypothesis means we have proved that null hypothesis is true, right? Sometimes what happens is we think that, we have rejected null hypothesis or alternative hypothesis. You can get confused. Whenever the p-value is less than significance level, your null hypothesis gets rejected. right? So now let's come back to the body temperature example, right? So now if you see this particular example, now like Anita ma'am, you have said, our hypothesis is that the mean, the ideal body temperature is 98.6. That is how it should be, right? We normally, when we check if it is roughly around 98 also, we are okay because we are approximating. But to be specific, 98.6 is the healthy human body temperature. So that is the null hypothesis. If it is not 98.6, it is the alternative hypothesis, right? So if you see the whole data set that we got, right, we'll check if it is closer to our hypothesis, or are we, for that particular data set, are we going to reject that null hypothesis, right? So now similarly, we are going to get the mean out of the whole body temperatures, 223 people's mean. Now we can see that the average body temperature is 98.16, right? Which is not, 98.6, it is lesser. Okay, so the average body temperature was a little lesser. But if we consider the significance level to be same 5%, we'll now have to know if the p-value for this is it less than 5%. If it is less than 5%, we'll reject the initial hypothesis that the mean is closer to 98.6 or mean is 98.6, right? So we are going to run the same function stats.test underscore 1sam, and giving the column body temperature and the hypothesis mean that we want 98.6. So I'm going to run this, and the output here is we got the p-value to be 6.46 into e to the power minus 27, right? So now what we are trying to do is, here I'm going to give two variables, because this number is very tough for us to calculate, right? Every time 10 to the power minus 27 and all. So now what we are going to do is, we are going to, because this is going to give us two outputs. One is the first t statistic and the p-value. Now I'm going to give t statistic and p-value, two variables. So I'm going to just get the output of this function and save it in these two variables, right? So let me run it. Now let's see what we have in these two variables, right? So we have the same numbers, t statistic being minus 12 and the p-value being 6.46 into 10 to the power minus 27. Now it is always difficult for us to check if it is less than the significance value. If the significance, we know that this threshold, the significance value is 0.05. Now what we do is, here we directly say, instead of trying to say if it is less than what is the actual number, we're going to directly say if p-value is less than threshold, then reject it. If p-value is greater than or equal to threshold, then we accept the null hypothesis, right? You don't actually have to know what is the actual value of the actual this is a very smaller value, 0.006. Yeah. So now if we run this, we'll see if the p-value is less than threshold or not, right? So now we can see that the p-value was less than threshold. It was far less than threshold, and we reject the null hypothesis and accept the alternative hypothesis as true, right? So the difference between the sample mean and the reference is statistically significant at threshold of, correct, threshold is significance, correct. So threshold here is nothing but the significance. Okay, I hope I spelled it right. Yeah, so yeah, if you remember, we have got this significance level 0.05, same threshold. It should have been significant. It would have been easier. Right, thank you, ma'am. Great. So now it is easier for us to know. Now in this body temperatures example also, if we take the significance as 5%, we can see that this particular data set, it is not coming closer. The actual body temperature is not 98.6. We were able to deduce that, right? So that is how we have done it, right? So now we've understood how we do this t-test with our Python function. If you've understood this particular function and know if when to reject, because you'll be able to reject when p-value is less than the significance of threshold, right? So if you understood how we have used this hypothesis t-test, this one samp function to do deduce, to know that if null hypothesis is true or not. If you understood that, type U in the chat box. Great. Thank you, Ravindra sir. Thank you, Suja ma'am. Thank you, Vinita ma'am. So what we have done one sample t-test, right? So one sample stands for that one sample t-test. The data was numeric. Okay, in Coke example, it was numeric. In body temperatures example, also it was numeric, right? So now we've understood how to do that any t-test on different data sets, right? So we first understood the concept behind all of these. Then we have understood there is a simple formula to go ahead and do that, right? So all of that is clear. Now this is how you do one sample t-test, right? So we are reaching the conclusion of the session now. So we also conduct hypothesis tests to compare means of two independent population, right? So you can always go ahead and compare means of two independent population. So here what we are trying to do is there is one data set which is called the brain head, right? What is the source? The source is a study of relations of the brain to the size of head, right? So basically the brain size relating to the size of head, right? So there's one study that someone has done. So not someone, some R.J. Gladstone has done in 1905, right? So we wish to determine if there is a relation between age, the brain weight in healthy humans, right? So that is what we are going to do here, right? Now we see the data set, the CSV file here. And so Raja sir, if you're there, yeah. So we've also shown how to import CSV files into Python in our previous sessions. You can also go there, so it will become easier for you, right? So we'll just try to see. Yeah, so there is gender. So you can see that one maybe for one gender, two for other gender, and age. So now there are two ages, 1 and 2, which means it is younger and older. So what they have done is younger age group and elder age group that they have done. The head and the brain weights that they have put, right? So they have given, right? So now let us go ahead and import that into brain data frame. We are creating a new data frame called brain_df, copying all of this into that particular data frame. Let's see how many rows we have. We have 237 rows and 4 columns. 4 columns we are clear. Now we know that there are 237: gender, age, head, and brain weights. So the brain size is measured in grams, right? So here it is 1.5 kgs, right? Okay. So now we have understood. Now age 1, individual was 20 to 46 year old. Age 2, wherever it is age 2, individual was 46 plus year old, right? So now what is the hypothesis? Null hypothesis in a 2 independent sample t-test, right? So we are going to do the two sample t-test. Let me see if we are going to do that. Yeah. So now we are going to do that. The alternative hypothesis is that the 2 population means are different, right? So the 2 population means are equal is the null hypothesis. The alternative hypothesis is sorry, really sorry. So the alternative hypothesis is that 2 population means are different, right? Means the younger population, the individuals which are between 20 to 46 year old, and the individuals who are over 46 year old, if the means of both the data sets are same, then our null hypothesis is true, right? So the alternative hypothesis is that both of them have different means, right? So that is what is going to be our hypothesis. So the hypothesis, null hypothesis, mean of first set and mean of second set being equal, right? Younger people mean and older people mean being equal is the null hypothesis alternative is not being equal, right? Okay, it is mentioned here. Very good. Now, what we are going to do, we can use the two sample t-test function, right? So we have used one sample t-test function. Now we are not going into the whole theories and all, right? We are directly getting into the, Python functions. So we can use the two sample t-test function to test for a statistically significant difference at the alpha equal to 0.05 level. So now alpha equal to 0. Is nothing but significance. If you remember, significance is denoted as alpha, right? So what they are saying is a statistically significant difference at the alpha equal to 0.05 level, right? So now we are importing numpy, and then we are from this scipy importing the stats, right? So which we have done previously also. Now we are going to see the head of the first 5 rows. We have seen that. Now we are going to create a new data frame. The name of the data frame is younger. And here what we are doing is we are filtering out from the data frame where the column age equal to 1, right? So what it is going to do is it is going to bring all the, so let me go ahead and print it. So instead of explain, right? So I'm going to say, let's say younger underscore dot head, right? So yeah, so it will only have ones, it will not have twos, because we have filtered out the column dot age equal to 1, right? So whenever you say this, out of this whole data frame, younger will come here, right? So then what we have done, then there's another command which said, now this was younger underscore. What we have done is we don't require all the other inputs. We are only going to use the column brain, right? So what we are going to do is we are going to create another data set younger equal to younger underscore only brain. So now if I'm going to get this particular data set, you can see that we only have one column, right? So let me make it simpler. So what I'm going to do is younger data frame, a younger complete, right? So let's say it is the whole younger complete data frame, just to make it easier. And out of that younger complete data frame, I am going to just get in the younger data frame only the brain column, right? So now you have understood that here we have only the weights of brains in younger. Similarly, there is older data frame which has the brain weights of older. We have taken both. Now here in older we have taken age equal to 2. Okay, age 1 or 2 is not saying they are a 1 year old or 2 year old. Here what we have said, age is 1 means he is between 20 to 46. Age 2 is, it's like a denotation. Age 2 is his individual is, he or she is over 46, right? So we are creating two data sets, right? Because our hypothesis is we need to get the mean of younger and mean of older and check if both of them are same. So that is where we have created two data frames, one younger, one older, and younger has age equal to 1, older has age equal to 2, right? So I hope that is clear, Vinitham. Great. Okay, so now we have our two sample set. Now the function here is stats.t_test_int. So when you do that, the sample, like if I hover on it, okay, so Vinitha ma'am says how age equal to became the younger age group, right? So now this whole data set that we have here, madam, where is our brains data? Okay, now we have in this whole data set, they have only ages 1 and 2. So what they have done is like how we have genders, in gender, if it is 1 means let's say they have male, and if it is 2, they have said it is female or something like that. So they have denoted it differently, right? How we have M for male and F for female. Similarly, age, what they have done, 1 for younger, 2 for older. So that is what they have done. They just denoted it by symbol 1 or number 1 or 2, right? So I hope that is clear, madam. Now, how it was filtered, right? So now to filter any particular data set, now brain underscore data frame, this data frame, let me remove the head. Let me try to run it, run the whole data frame. Now in this whole data frame, there are ages 1 and 2, right? Okay, so it does not mean age 1 or 2. It means there are ages with denotion 1 and 2. Yes, Sujama. Sujama, you got it right. Yeah, so I'm just explaining. Now, age 1 means, yeah, so let me copy this. Ma'am, you have sent it directly to me. I'm going to send it to everyone. So 22 to 42, 46 meaning being 1, 46 plus being 2, right? Okay, so thank you so much, ma'am, for bringing that, right? So I've just added it, right? So Vinita ma'am, I hope this is clear. Now, how we have filtered it is, first we have taken complete. So when you can use this command, if you remember how we used to filter by some condition, right? So like less than, greater than, right? Correct. It is a classification, right? So that is the right word. Maybe I did not catch it. So it's a classification. One is for younger, 2 is for age groups 46 plus, right? So now if you remember in our initial sessions, whenever in a column you give square braces and say the name of the column and give it a condition, it is going to bring back those results, right? So let me go ahead and do that. Now, if I'm going to do this, it is going to bring me only once. Now, if you see here, in the actual, we had ones and twos, but when you filtered it, it gave you only once, right? So now there are 110 people who are younger, right, in this data set, right? So now what I have done, because I have to do means every time, I have created a new data frame and called it younger complete, right? It's a full data set of younger people. Now, then later what I've done, I have created another data frame younger and said, I don't want all these gender, age, and head. I'm concerned with brain. Just give me the column brain, right? So out of this whole data set, give me younger, right? So then I have created younger data frame and I have just printed, if I just print younger, it is going to give me only the brain weights data, right? Similarly, if you do 2, it will give you the second classification of data, right? I hope it is clear now, Vinita ma'am. Great. Okay, so now like how we had the one sample, function. Now we are going to do this. Okay. Yeah, you can. Okay. So I think this is more of a syntax question. Let me just go ahead and see if, because we are trying to take one column, if it is going to work. Yeah, it is working, madam. So, because the syntax even works for one or more columns, so you can go ahead and even do that. Right. So I think that was your follow-up question. Thanks for that, ma'am. Great. Okay. So let me see if it is worked, right? So it is working. Great. Thank you so much, ma'am. Now, our 2 sample t-test, how it works is you give the first data set younger, then say second, the data set which is older, and then we are going to say equal underscore var equal to false, right? So let me go ahead and hover on it to get, right? So now you can see that the definition says A and B and equal verify equal to true. So let me go and read the definition, right? So like, let me just say if false, performs the t-test which does not assume equal population variance, right? So because we don't have so it is true, perform a standard independent two sample test that assume equal population variances, right? So basically here we are saying false because our population variance is not same. So we are going to say equal variance equal to false. I'm going to run this. Okay, so now it has given two results. It has given us a p-value and a t-statistic value, right? So similarly, now we are going to run, we are going to do a plot of the same, right? So you can go ahead and plot the younger. Okay, so let me do that. Younger complete data frame. And let me just go ahead. Right, so you can do a dist plot on the first data frame given color as red, right? If you remember the plottings that we have done earlier, right? So let me go ahead and first plot, right? So now you can see that there are two plots that came in. One is in color red and one is in blue, right? So you have got them. And now what you're doing here is you're saying add vertical line where the mean of younger is there and the mean of older is there, right? So I'm going to also add those vertical lines, right? So now you can see that the means are different, right? So what was our initial hypothesis, right? So the initial hypothesis was that both of the means to be equal. So the p-value is 0.009 after rounding. We reject now we reject the initial hypothesis at alpha 0.05 because p-value is less than our alpha significance level, and we conclude that there is significance, the statistically significant difference in the mean brain weight between individuals younger than 46 and individual over 46, right? So you can see that here whatever the mean is there is different in both the groups that we have, and so that is the reason we are rejecting the initial hypothesis where we thought both of them could be equal, right? So this is what we have done here using the second function, which is t-test underscore ind, right? So if you remember the first function, it was, let me go ahead and so the first function was t-test underscore one sam, and this next function is t-test underscore ind, right? So you can use this both functions to be able to do our one sample t-test and two groups. We had two groups here, two sample t-test also, right? So important thing to remember is whenever your p-value is less than the significance, whatever the significance has been mentioned, then your initial hypothesis, whatever is there, it is going to be rejected. Great. So so if how we have done the two test, if this was clear, type C in the chat box. Thank you, Sucha ma'am. Great. Thank you, Vinita ma'am. So now we have understood the concepts of t-test. Thank you, Ravindra sir. Now what we have done is we've understood the concepts of these, which helped us in testing the hypothesis, right? So we have tested if Coke was, the fountain Coke was closer. In our case, nowhere the initial hypothesis was true, right? And we have seen that the body temperature is not closer to 98.6 in the sample set, right? So meaning that it was not a fully healthy, sample set, or I mean, temperature wise, according to the initial hypothesis. And then we have understood the third example of two sample data sets on these two groups, younger and older, based upon their brain weights. Yeah, so we've also understood that also where there the initial hypothesis was not true. Yes, so one more emphasis on common mistake. Yeah, great. So we are here, Ravindra sir. I just have to, double check and maybe, come back here. So now you see common mistakes. What happens is now because p-value is very much less than 0.05, we fail to reject the null hypothesis and conclude that the mean caffeine content is not 34 mg. Failing to reject the null hypothesis means we have proved that the null hypothesis is true, right? So this is what I think brought a question to you, because here it says null hypothesis is true, right? So I think that is what your question is, Rendra sir. Yes, I think I also got the query. Let me confirm that tomorrow, right? So I think it's a typographic typo error or general error that was done while the file was created. So this is a manually created this thing. So let me confirm on that. Thanks for that. Yes, sir. But by large, we know that if p value, even if you go through JS's lecture also, you'll be able to see that his the statement is you are rejecting the null hypothesis because it is less, but here it says it is true. Maybe there is a play of words here, failing to reject, which is what you call minus of minus, something like that. So let me come back on this tomorrow, right? So I'm also not pretty sure there. It could be a simple change of text. Great. Okay. I guess apart from this, everything was clear. Thank you, Suji ma'am. Thank you, Vinita ma'am. Thank you, Ravindra sir. Great. So now, okay. Now till our previous sessions, we had more of a single way interaction, but failing to reject is accepting null hypothesis. Correct, Vinita ma'am. Correct. Yeah. So I think it is based upon context, and Ravindra sir, I think here they are not talking about our example where the null hypothesis is the Coke being closer to 34 milligram. It is in general. Maybe the statement here is failing to reject is accepting null hypothesis is in general that has been mentioned, where somebody thinking failing to reject might be false, might be saying that it is false, but it is actually true. So that is what might have been mentioned, but I'm not pretty sure here. So I'll come back on this. I think Vinita ma'am, whatever you're saying is in a general context. So we'll go ahead and confirm that tomorrow. Great. So I know it could be a little overwhelming if it was, if it was more of text heavy than how we do more of commands and all, right? It is based on the example here. Yeah. Let me confirm that. Yeah. Thank you, Ravindra sir. Right. So I would request someone to unmute or maybe come on camera and share the feedback on how the how the understanding was, and maybe a few things that you felt were interesting, right? So if somebody would be open to share the feedback, would be glad to hear. Yeah. So any result, like basically you did not know hypothesis testing before. Now you came to know. So what is the difference? What is the result change that you have got out of this session? So considering more than feedback, it is the result sharing, right? So I request anyone to go ahead and based upon this particular specific module that we have covered or revised, what is the difference that you had before session and after session? Yes, sir. Ravindra sir, go ahead. Yes, Suju ma'am. Yes, please go ahead, sir.
Yeah, just we were aware of most of the concept, but it is graphically telling and it becoming more clear. Long back we went to the statistics classes and that, but most of them were a little bit needed reinvention, and the way it is given and graphically illustrated, it makes more clear also and interesting. Now that we will be moving to the next stages, so it helps us to get more clear about this.
Thank you so much. So really like the way you've taken it actually as a revision of concepts that were learned long back. Thank you so much, sir. Yes, that was really, yes, ma'am. Please go ahead. You're on mute, ma'am. Yeah.
You have very well explained. The first thing is the problem itself you explained very well rather than going to the numbers initially. That is the part which I liked the most, because once you have understood and what is a thesis hypothesis, whether it is a null hypothesis, once you get that point clear, then the rest is sort of just looking into the numbers, and anyway it is more or less like automatically it is derived.
Yes,
so well, very well explained. And
Thank
of course the samples and the numbers added on to it.
Thank you so much, ma'am. And it was very well received also.
Yes.
We can see your active participation in all the sessions. So thank you so much, ma'am.
Thank you so much.
Yes,
You are
ma'am.
taking lot of trouble, lot of efforts in explaining also. That is very well appreciated.
Really, thank you so much, ma'am. Yes. Yeah. So Vinita, ma'am, also you put it on chat, ma'am. Would you be interested in coming up online and sharing it?
Yeah, your revision sessions are making the concepts more clear, and it is getting that everything is getting more clarity after your classes.
Yeah, thank you so much, ma'am. Really thanks for the input. Okay, thank you so much, everyone. And I'll also get back if there's any other queries also coming up. So we'll also meet tomorrow for another hackathon. And as we proceed, the coming week, maybe we will have a change. Like right now, we were having Tuesdays, Fridays, and Saturdays. Maybe we will be tweaking that schedule, and maybe we'll be, making it Thursdays. We will be going to, we are going to put it on the way on email as well, right? We're going to make it Wednesdays, Fridays, and Saturdays. Yeah. So we're going to make it Wednesday, Friday, and Saturday. Yeah. So you can expect it to be on the same schedule. We'll also be mailing about it. Great. Thank you so much, everyone. Thank you, Suju ma'am, Vinita ma'am, and Ravi sir for all the.
Sachi, I don't know your email. I would appreciate to get your email.
You can send all of the emails. So basically, team has access to,
Okay, all of you have. Okay.
all of it to J at Pixeltests.
We send to J always. Yeah,
Correct.
that is accessible to the whole Pixels team.
Yes,
Yeah.
yes, madam. So what happens is we have a system where mails go to the respective people. So you can directly send it to J at Pixeltests.
Yeah, good.
Yes, thank you so much, ma'am.
Yeah.
Thanks, Anita ma'am, Anil sir, Raja sir, Operation Monica. Thanks, everyone. See you all. See you.